Alright, welcome everyone. Tools of Operations Research. This is lecture 7, so the last lecture of the term. And before we get started on any new material, we're going to step back and go over assignment number 6. We'll kind of work out parts of it ourselves here live. So I have assignment number 6 up on my screen. Let's just kind of start building the model and working through how you would answer the parts to the first problem, the first exercise. So it says a firm uses the policy of ordering 2 particular items at a time because they come from the same supplier. The characteristics are shown in this table. So we're going to be ordering some of these items. There's a fixed cost for every order. So every order there's an overhead you pay for that order of $3 for both items. Okay, regardless of how many of them you're ordering. And then obviously there's a unit cost and a holding cost or a holding percentage of that unit cost, which is how much do we have to pay to keep that item in stock on hand. And obviously we have a demand of how many we need to have throughout the whole year. So we've got to figure out how to order items 1 and 2 such that we end up ordering over the year 800 item 1s and 40 item 2s to minimize costs. And like we worked through last lecture, there's basically the fixed cost portion of this in how many orders you make per year, but then there is also the inventory cost, which is how many items you have on hand on average multiplied by their holding cost, which is the percentage of a unit cost. So we'll go into Excel and start working through this. So I'm just going to item 1 and item 2. I'm just going to copy all the parameters of the problem. So I think item 1 said we needed 800 a year, item 2 we needed 40 a year. There's the fixed cost, which is both $3. The unit cost, which was $10 and $12, and the holding cost, which was 30%. Okay, so these are currencies. We'll make them look as such. Okay. So what we need to do, so we're going to solve this is going to be a nonlinear optimization problem. The reason it's nonlinear is the equations we're going to use, which will be apparent in just a minute. And obviously we're doing optimization because we're trying to decide optimal values for some sort of decision variables. In this case, what we're going to be deciding, so our decisions to make are, you can either do it number of orders per year or the quantity of how much to order, because obviously with one you can always compute the other. So let's just do quantity of how many item 1s and how many item 2s we want to order. Let me actually do it this way, item 1 and item 2. Okay, so let's say if we decided to order 800 item 1s and 40 item 2s, then we're deciding basically to order the entire amount we need in a single order. Okay, probably isn't best, but let's find out. So those are our decisions that we're trying to make. So let's look at some calculations we'll need to do as well. So since we're deciding how many to order, we can compute the number of orders we'll need for the whole year. And that's just going to be, well, if I needed 800 item 1s for the whole year, and I divide that by how many I order at a time, that gets me the number of orders, which obviously is 1 here. Okay, and same thing for item 2. Okay, oops. Let's see, divided by, there we go. Okay, so that gets me the number of orders I make per year. From that, we can compute our fixed cost, or fixed costs, because our fixed costs are just the number of orders we make per year times the fixed cost per order. Okay, so the number of orders we make multiplied by the fixed cost per order. So that's how much cost there is just in the overhead of orders, making orders. Okay. But then we have an inventory cost. Okay. And the inventory cost works something like we have to know how many items we have in stock on hand on an average day throughout the year. And we'll assume, just for the sake of making it simple, that if we ordered, say, 800 item 1s, that we'll sell them at a linear rate, which means throughout the whole year, on average, we'll have about half of that on hand. Okay? And if we have half of that order amount on hand for any given day, we'll multiply that by the unit cost and holding percentage of that unit cost. Okay? So multiplied by those two numbers to determine inventory cost. Okay? So we're going to take this number divided by 2, multiply that by the unit cost, multiplied by the holding cost. Okay? And that gets us our inventory cost for that item. Okay? So obviously the inventory costs for item 1 are much higher because we need more of them. We'll have to keep more of them on hand on any average or given day out of the year. Okay? And from there, we can compute total costs by adding fixed cost to inventory costs, and then between both items we can get to our final costs. Okay. And that will be the objective we want to minimize. Okay, it's total cost of everything. Okay. So let's use Analytic Solver Platform and set up the equation, or sorry, the optimization problem. So here are our two decision variables. Here is the objective we want to minimize. Okay. And what we need to ensure you can think of it in a few different ways. What we need to ensure is that we have to order something. In fact, we need to order enough that we can meet the demand for the whole year. Okay. Now, obviously, if I were going to minimize costs, technically, right, I can minimize costs by doing something like ordering nothing, and you either get 0 or because of divisions you get nothing, okay, or not a valid number. But it's enough to say that we will constrain our decision variables to be positive. Okay, so we have to order a positive amount in order to know how many orders to make for the whole year. If we order a positive amount, we'll have a positive number of orders, which will make all the costs work out to be positive. Okay, and we're just wanting to minimize costs, but we're going to constrain that. Obviously, we can't do anything like order a negative amount to get negative costs, right, in order to minimize them. So I think it would be enough in our engine that we can just say that we will assume the decision variables have to be non-negative, and as they have to be positive. Okay. Okay. Any other thing? Does anybody know of anything I missed? I think I captured all of the parameters correctly. Yes.
Products have to be equal.
Oh yes. So for part A of the problem, we're going to constrain that the number of orders we make over the whole year are going to be equal to each other. Okay. In part B, we'll relax that. But part A, what we want to say is we're going to add a constraint to say the number of orders for item 1 here in cell C10 is constrained to be equal to the number of orders for item 2 in D10. Thank you. So that's part of part A of the problem. All right, so from there I think we're ready to solve. I'm going to select that we want the linear, or I'm sorry, the nonlinear engine. So the LSGRG, the large scale generalized reduced gradient nonlinear engine, and then we don't have to automatically select one. So solve. Oh, okay. It was not enough that we selected it to be non-negative. We need to constrain that these be greater than or equal to, we can do 1. So obviously you can't order less than a fractional amount. You can only order a whole amount of items. Okay. So I've added that as a constraint. So it's not enough to say non-negative, because it still found it could use 0. That was a legal value to try, but that resulted in illegal or non-numeric results. So we need to constrain that we order at least 1 of each item at a time. Now we can solve. Okay. Now, the problem did not say that we needed to constrain these to be integers. It might make sense, obviously, although you'd probably find that there's no such integer for some cases that you could order the item 1 and item 2 in some whole number amount that would also make the number of orders per year come out to be equal. So we'll say this is close enough. Okay, so we're ordering something like about 55 item 1s and 3 item 2s at a time for roughly 14 and a half, or let's say about 15 orders, 14 to 15 orders for the whole year, okay, for the minimal cost of $175. So our part A answer is that we would order, we'll just say about 55 item 1s and about 3 item 2s for a minimal total cost of $175. Okay, so that is the answer we would have to the part A. Find the optimal cycle length for the joint orders. Joint meaning that we're going to order them at the same time, so we need the same number of orders for the whole year. And then what are the optimal order quantities of the 2 items? What's the average annual cost combined? Okay, so that's what we've answered. So part B says, suppose now that the 2 items are managed independently and each can use its own optimal order quantity. That is, we won't constrain that we have the same number of orders for the whole year. Can we get a better overall cost without that constraint? Okay, so easiest way to do that would be to come to the Model tab of the Analytics Solver platform panel over here and just uncheck that constraint that we added to say that C10 must be equal to D10. That is, the number of items or number of orders for item 1 is equal to the number of orders for item 2. So that's so with that unchecked, that's no longer a constraint of the problem. Okay, so we can resolve. And sure enough, what we found was we would order something like 40 item 1s and 8 item 2s for a minimal total cost of $149. Okay. And then finally, if we look at part C, suppose that there is a savings in the fixed cost due to the joint ordering. So if we order jointly, basically instead of paying a total of $6 of fixed costs, we could pay only $3 by ordering jointly. So there's some savings if we do order jointly. Would that be better? So which strategy, the joint ordering with the lower fixed cost or the independent ordering, would be preferable? Now, but we already know from part B that the independent ordering gets us a minimal cost of $149. Okay? So really in part C what we want to just say is, what if the fixed cost, total fixed cost, was, instead of these two added up, was just half that much? Okay? Now there's an infinite number of ways you can do this. Okay? I'm just going to zero out one of the values. Okay? Because essentially what that says is, choose how many items you want to order, we'll calculate how many number of orders we'll have, and then we'll add up all the costs, but we're only going to have fixed costs for item 2, not item 1. Okay. Again, assuming that we're going to do joint ordering. So again, I'm going to add back the constraint that we have to order such that we have the same number of orders, because we'll basically not pay fixed costs for one of them. Okay. You could have done this by making both of those numbers 1.5. You could have done that by coming down here in our calculation and dividing it by 2, or whatever. Okay. But just zeroing one of those fields out is enough to affect what we want. Okay. So now the answer to part C is going to be, okay, is it better to order jointly for the lower fixed cost or independently with the higher fixed cost? And in fact, we see the lowest maximum, or the lowest total cost is better if we order jointly by only paying a $3 fixed cost instead of $6 fixed cost. So I would say something like, it's better to order jointly at let's say 39 item 1s and 2 item 2s for a minimal total cost of $124. Okay. So obviously $124 is less than $149 that we had before, okay, with the non-joint ordering. So that's how I would go through this problem, equations, the answer to the parts. Are there any questions about that? How that worked out? Okay. Do be sure on assignments that you do take care to note if it asks for things like, here it was asking for the optimal order quantities, and it was asking for the average annual cost or the total cost. So a full answer to part A needs to include all of that information. Don't assume necessarily that I can go through and get that out of your model, right? Spell that out so that I can see that you can read it off the model. Basically, I want you to be able not just to build the model, but to be able to interpret what it's telling you and pull out the relevant parts. Okay, any other questions about assignment 6? Doesn't look like it. Well, there's pretty much the answers to half of assignment 6, but you only have a few hours left to do it, so I think that's fair enough. Okay, we're going to move on then and talk about one last topic for the term. So before we do that, let's take just a short break, clear some things up, and then come back and talk about